Right, this is the third and final video on the quantum mechanics topic. It's about wave-particle duality. Now it makes use of a wonderful equation that was given by Bohr when he put his PhD thesis together. And I'm just going to show you what it was. So Bohr said that the wavelength, well, essentially, the reason why it's wave-particle duality is that any particle has an associated wavelength, and any wave-like nature has an associated particle. And you've already seen light wave as a photon, but what we're going to explain is how an electron, which is very notably a particle, can be like a wave. And Bohr said this is extended to all types of particles, in actual fact, and the way that you work out their associated wavelength is Planck's constant divided by the momentum. And from your work in GCSE, I'm sure you can remember that the momentum is the mass times the velocity. Now I'll show you he didn't just pluck this out of fresh air. There is an associated proof with it, but a generalized one. And let's just draw your knowledge from the energy of a photon, which is hf, which you can rewrite as hc over lambda, because you know from the wave equation the frequency is the speed of light divided by the wavelength. And what you need to know, and that's why it's generalized, is that the momentum of a massless object is equal to the energy divided by the speed of light. So let's put these two together. Energy divided by the speed of light, which gives us our momentum, is equal to hc over lambda divided by the speed of light. Of course, those disappears, and that leaves us with h over lambda. A slight rearrangement gives us what Bohr had stated. His PhD was not that simple, by the way, but nonetheless, it gives you a slight proof of massless particles as to why we reach this point as we do. So let's give a few equations then. Let's work out the wavelengths of some associated particles and vice versa. So, first of all, let's look at an electron moving at 10% the speed of light. What's the wavelength for this object? It's a straightforward equation. If you think you know, hit pause and then give it a go. There's 2 bits of data you need to know, and I think you ought to memorize this if you're this far into the course. But let's just state those again. The mass of an electron is 10 to the minus 31 kilograms, and of course h, Planck's constant, 6.63 times 10 to the minus 34 kilograms. So let's do the maths then. Oh, and you need to know the speed of light, but hopefully that is very easy to recall. Good. So, what's our wavelength? Well, our wavelength is going to be h over p, h over mv, which gives us 6.63 times 10 to the minus 34, divided by 9.11, 10 to the minus 31 by, and now we're at 10% speed of light, so 0.1. That should give us, when we plug all those in, let me just find when I did that previously, we're looking at about 2.43 times 10 to minus 11 meters. Okay, so incredibly small. Not too small to notice, but incredibly small. Okay, that was example 1. 2. Let's go for a human being, because there's no reason why they do not have a wave-like nature to them. I should probably spend longer on this idea that a human might have a wave-like nature to them. But when you look at a 70-kilogram person moving at 2 meters per second, their associated wavelength is going to be, well, hit pause if you think you know how to do it. Otherwise, let's quickly look at it h over p, which is 6.63, 10 to the minus 34, over 70 times 2, and that gives us, oh, this is incredibly small, 4.47, 10 to the minus 36 meters. So small, there is no wave-like behavior that's exhibited. So therefore we can say it doesn't really happen. Though theoretically it does at an incredibly small wavelength. It doesn't really happen. Okay, so lastly, okay, let's do this reverse. What's the mass of a photon of wavelength 700 nanometers, which is a red photon? Now we know they're massless, and therefore this is a bit arbitrary, but let's work it out nonetheless. What do you think the mass of the 700 nanometer photon is? If you think you know the answer, hit pause. Otherwise, here we go. Well, the mass times the velocity is going to be h over lambda. I've just rearranged this equation up here. And so therefore we can say the mass is going to be h over lambda times the velocity. That's right, being the speed of light. Because we know they move at the speed of light. 34 divided by 700 times 10 to the minus 9 by 3 times 10 to the 8, giving us yeah, 3.16, 10 to the minus 34 kilograms, which in effect is 30,000 times less than an electron. So we can say that the photons are massless, in effect. Good, okay, so now most questions that you'll be asked will just ask you to deal with that very simple calculation of what is the wavelength of, what is the momentum of, what is the energy of, perhaps it's all dealing with this equation here. So, what we need to do next is a little bit more advanced, but I'm keen on showing you how this can be used and proved. First of all, it's worth saying, yeah, how do we prove this? Probably what's been shown to you before is the idea that if you, especially with electrons, wave proof, if you fire electrons at a piece of graphite, then on a screen, what you see these circular bright patches and dark patches. Now these are very characteristic of a diffraction pattern. Now diffraction patterns, we know, illustrate wave-like nature. Electrons, we know, are very much particle-like. So therefore, what's happening is this electron is behaving very much like a wave. Why is that? Well, the graphite is actually a series of layers of which you have these hexagonal, oh that's a terrible hexagonal structures. And this presents an aperture to the electron, which means you get diffraction taking place. You can do some sums to work this out, which we do in class, and it yields some pretty good answers. And you can work out quite happily the wavelength of your wave that you have created from your electron. However, let's put together a few more nuts and bolts. Remember, this is just extra, but some more nuts and bolts. In order to create that electron and get it moving, what you need to do is you need to make a cathode, which is negative, and an anode, which is positive. And as the electron that is bubbling off the cathode moves towards the anode, the kinetic energy that it gains is equal to the charge on the particle, in this case an electron, multiplied by the voltage that's applied between it, or EV. So there is a way in working out the velocity of your electron as you accelerate it from one plate to another. In actual fact, if I rearrange this, 2 EV over m square rooted gives me the velocity of the electron. In turn, from my velocity, I'll be able to work out the wavelength, like we did before. And then if we know the wavelength, and you are familiar with diffraction, we should be able to work out the spacing of the hydrogen atom. Sorry, what am I talking about? Of the spacing of this graphite hexagon that's pulled into place there. It's something that I'm going to go through and just explain, but two consequences from that equation first. I'll write that down. First of all, if I have if I accelerate this electron between two plates, and I know that the velocity of my electron is 2ev over m square rooted, as shown before, and I want to work out the wavelength, which is h over p, h over mv, h over, rather large equation here, hold on, 2ev over m, h over root 2evm. What this means is that the wavelength is proportional to 1 over root v. If I were to increase the voltage, I can decrease the wavelength. And this is used in electron microscopes. In order to better resolve an image, you need a shorter wavelength. So I can control that wavelength by controlling how fast I'm applying my voltage between the two plates. Okay, so what we want to do now is, let's imagine our setup of our graphite, greatly magnified, diffraction pattern, and then this set of rings that occur due to the diffraction of the electrons. If I were to measure this displacement there, if I was to measure the length given there, and if I were to know what the voltage were of my electrons provided, that would give me a velocity of the electrons, and therefore a wavelength, an arrow because it's not equal to. Then I could work out, hopefully, the aperture, because I know that A sine theta gives me n lambda. So let's see what I can do there then. I did the calculations before, and I came up with x being about 1.5 centimeters, L being 14.5 centimeters. My accelerating voltage was 5.48 kilovolts. This is the first maxima, and so therefore, let's plug it in. Lastly, of course, sine theta is approximately tan theta for very small angles, which gives me x over L. I'm sure you've used that in the wave topic before when you've done diffraction, young slits. So if I plug it all into the same equation, what I come out with is saying that A is n lambda over sine theta, n lambda over x, L at the top. And I know my expression for lambda up here. That gives me a rather large equation, hold on here, h over the root 2mev by L divided by x, because I'm looking at the first maxima here. And that gives me 6.63 times 10 to minus 34 by 14.5 centimeters. It's a quick conversion, divided by the root of 2 by 9.11 times 10 to the minus 31. Mass of charge on the electron by the voltage, 5.48 times 10 to the 3. Square root all of that. and multiply it by, well, let's just put 1 over 1.5 centimetres. Grand total of 2.5 times 10 to the minus 10 metres, and that is right for a graphite separation. Good, so that's quite a pleasing experiment. But essentially, just bear that in mind, if I can control the voltage, I can control the wavelengths, hence electron microscopes. Another little extra here is what Bragg did to confirm this theory is true. This might be quite nice, it's sort of synoptic as well. What they did was they fired electrons at nickel, and nickel has a nice regular structure. As these electrons came in, the one that bounced off the surface, reflected should I say, the one that bounced off the layer below, electrons nonetheless. What took place here was there was a certain path difference which was covered here and a path difference there. And if those two path differences, so the path difference, two lots of those path difference equals to a whole number of electron wavelengths, then constructive interference was seen. Now they knew the separation of these nickel plates, D, nickel layers in the crystal, they knew that quite well. So what they did was they brought in electrons at a velocity of 5.9 times 10 to the 6 meters per second, controlled by a voltage. They knew the separation was, and what they were looking for was to see whether these constructive effects gave rise, whether this value for lambda for the electron gave rise to a similar value for D, because which they knew. So what they did was they said that the wavelength was h over p, electrons of course h over mv, 6.63 times 10 to the minus 34, 9.11 10 to the minus 31 by 5.9 10 to the 6 gave us something like 0.12 times 10 to the minus 9 meters. I haven't double checked that, so I hope that's about right. And then they worked out that the path difference, which was covered, the path difference is going to be equal to 2 lots of d sine theta. This is, the incoming ray was running at theta, so therefore we have theta, and opposite over hypotenuse gives you sine theta, so opposite, path difference over d, sine theta, and you want 2 lots of that, and they knew the separation was running at, they knew this was taken at, I think they were looking at 50 degrees, so therefore 2 by, and the separation of the nickel was, oh, it escapes me now, I think we were running at 2.15 times 10 to the minus 10 sine of 50 degrees gave us something like 1.65 times 10 to the minus 10 meters. Not that dissimilar. So they had a wonderful proof. Bragg experiment. Anyway, like I said, pretty advanced stuff, not to worry too much about. Okay, finally, the last idea. This really helped, the idea of Bohr really helped this idea of the Bohr atom. The Bohr atom, remember Rutherford's atom said that if you had an electron orbiting, the problem was they knew it would spiral in and it would implode. So why did atoms not implode on themselves? And Bohr said, well, what happens, Bohr's assumption was that if the angular momentum was a whole number of a constant, this was his hypothesis, then the electron would exist in a certain state. He actually said the angular momentum is mvr, the momentum times by the rate of the angular momentum, a whole number of h over 2 pi. Okay, so this was his hypothesis, the Bohr atom. Now what de Broglie had shown was this electron was a wave, so what happens is these actual electrons exist at points where there are standing waves in atoms. And if there are standing waves at these points, then you can say that the circumference of this radius has got to be a whole number of the wavelengths of that electron. You know, of course, that this gives us h over p, which is h over p, and therefore, without too much movement around, we can then get to we can then say, well, p by r, so I've taken the 2 pi with me, is nh over 2 pi. And of course, p by r is exactly the same as this, so actually this proved Bohr's atom theory. The fact that they are standing waves is critical because in a quantum mechanical sense, the probability of finding an atom is equal to the amplitude squared. Because this is a standing wave, it has a high amplitude, so there's a high probability of finding this orbit. Here, it's the wrong length to make a standing wave, so therefore the amplitude is going to be very small, and therefore the probability of finding it is not there. That is why the electrons are found in only certain orbits. It's the heart of quantum mechanics, quantum theory, and moving on from de Broglie, Schrödinger showed that actually you can apply wave mechanics to the entire system. Anyhow, just coming back a little bit on all of this, what you should probably be most aware of is not the proof, just the equation. You can do the equation, that's great, in the sense of working out the examples, and then appreciating the diffraction pattern gives evidence of it. You don't need to worry about this, but I hope the rest of it was very useful and interesting.